Hello everyone, so in today's video I'll be talking about computing power from the 1970s to 2023. So let's begin. The basic component to a central processing unit or an integrated circuit is something called a transistor, which you could see right here. And this was the world's first transistor, which was created at Bell Labs by three engineers. First one named William Shockley, Walter Hauser Bratton, and John Bardeen. And this transistor basically revolutionized the world because before we had the transistor, we had something called a vacuum tube, which you see right here. And as a result, computers and electronics before the transistor era were very, very big. Vacuum tube radios were very big and clunky. I did see some back in the 1980s when I visited my grandparents' house. They had a vintage 1940s radio at their house. It was pretty big and bulky. And the transistors basically allowed companies like Sony Electronics, which pioneered transistor radios, to produce relatively inexpensive and compact radios which you can put in your pocket. So basically a transistor is a component which has three parts to it. So this is a basic transistor. It has a collector, base, and an emitter. And there's two different types of transistors. One is called NPN transistor and the other is called PNP transistor. So depending on which type of transistor that you have, the flow of electrons either goes into the base, like in this one, or it goes from the transistor, from the circuit to the base. So it goes in either direction, basically. And I'll just demonstrate to you in a very simple way what a transistor does. So transistors can be used as a switch. In computers, it would be called binary code. 1 for on and 0 for off. And when your CPU uses transistors, let's say it's forming this image on the screen, it has millions of light bulbs, millions of little diodes or whatever, or LED things on the screen, which is going on and off at a specific pattern to create this picture, right, on the screen. So I'll demonstrate it very simply in this diagram. I don't have to have this transistor to turn on this light bulb. I could not have a transistor here. As long as I have it connected to a battery, it would be on. However, if you would like to use the light bulb to do something more specific, you could use a transistor. And this is a collector, this is an emitter, this is a base, and as you can see, this is a circuit, and basically I could put a transistor here, and I could connect it to the base part, to a battery. It does require a small amount of electrical power for it to operate, like I think 0.7 volts or something like that. And basically what it does is I could use this transistor to put in a switch so I can turn the light on and off, or I could put a microcontroller or something to regulate it with a timer, so I could tell it to turn on and off at a specific time. Or I could use a sensor, like I could put my hand near the sensor and it would turn on when I touch the sensor, and when I take my hands off of it, it would turn off like that. I could use a sensor, microcontroller, whatever, or switch with this transistor. Or I could use it as an amplifier like this. So I have a microphone. Right now I'm using a microphone to record this, and I could put in a transistor right here. And basically, with the transistor, I can amplify the signal when it goes out of the speaker. So this wavelength has a low amplitude. Amplitude is the height of the wave, basically. And this has a low amplitude when I speak into the microphone. However, I could go to my speaker and I could amplify the image with a potentiometer. And speakers have potentiometers, which you could use to increase the amplitude of the output signal or the sound signal. And a transistor could be used to do that, basically. Like in this diagram right here. So transistors are an essential part of computing. And before they had transistors, they were using vacuum tubes. And you could see that ENIAC computer from the 1940s, it's very big. It takes up the size of a room. Not very compact, not very powerful. It probably has less power than a Commodore 64, which was released in the 1980s. That big ENIAC computer has less power than an Apple II or a Commodore 64. And basically, the next stage of development was called the integrated circuit, which was invented in 1958 by a man named Jack Kirby. This is a very crude integrated circuit. So you have a lot of transistors in an integrated circuit. That's what an integrated circuit basically is. And this is another simple integrated circuit of 1963. You have about a number of transistors inside of it. Instead of having individual transistors, you could just put it all into an integrated circuit. And when we go into the 1980s and stuff, 1970s, I'm sorry, we have CPUs like the Intel 4004, which has about 2,300 transistors in a integrated circuit. That is a lot. I mean, compared to what they had in the 1960s, right? And basically, what computer engineers want to do is they want to decrease the size of the transistor so they could put more transistors in an integrated circuit. So the more transistors you have in an integrated circuit, the more powerful the processor is, basically. So in 1971, we had the 10 micrometer process or node. So one micrometer is 1/1,000,000th of a meter. So in scientific notation, that'd be 1.0 times 10 to the negative 6. A billionth would be called a nanometer. That would be 1.0 times 10 to the negative 9. Or you could say 10 times 10 to the negative 8, if you want to put it in that notation. So that's basically what a micrometer is. So in 1971, they had 10 micrometers. And in 1976, they had 5 micrometers. So as this number gets smaller, the transistors get smaller. And then we go to nanometers after that. So in 1985, we had the 386 at 0.8 micrometers. And in 1993, we had something called a Pentium processor, Intel Pentium, at 0.8 micrometers. And as you can see, as time goes by, the nodes get smaller and smaller. So in 1998, we had the Pentium 2 with 7.5 million transistors at 250 nanometers or 0.25 micrometers. And as you can see, the number of transistors are increasing as the node process is going down or shrinking. So now we have up to 3 nanometers, or that'd be 0.003 micrometers, and it has 17 billion transistors in it. We also have something called a GPU, or graphic processing unit chips, like this from NVIDIA. This is a NVIDIA 8102-250 GPU, which is used in the GeForce RTX 4080 and 4090 series of graphics cards. Very powerful cards, and this has about 76 billion transistors, much more than this. It's capable of 82.58 teraflops. So in a teraflop, there's 1,000 billions in it. So it's 8,258 gigaflops. And a gigaflop, there's 1 million. It's times 1,000 millions in it. So that'd be 8,258,000 megaflops. Okay, very, very powerful. And back in the 1980s and 90s, we had something called a math coprocessor. This is a chip that you can put into your motherboard, which would increase the math calculation potential of your machine, making it more, I guess, faster. Kind of like how a GPU assists your CPU when you're doing graphics intensive stuff like AutoCAD or playing 3D games or whatever. But GPUs are much more than that these days. It's used for artificial intelligence, scientific modeling, and stuff like that. A lot of scientific researchers use GPUs these days, and countries also use GPUs to make stuff like supercomputers and stuff like that. So very important part. And as you can see in this graph, the transistor count. This is the graph of transistors in CPUs from 1971 to 2023. And this y-axis or vertical graph is scales from 2,300 transistors to 17 billion transistors. And this x-axis or horizontal axis is from 1971 to 2023. And as you can see, technology was pretty stagnant in the 1980s, 1990s, and starting from the 2000s, it just started to take off exponentially. We had better nodes, better DUV lithography machines, or DUV is deep ultraviolet lithography machines. These are the machines that you use to make CPUs. And it's been getting more expensive and more complicated over the years. So a lot of companies dropped out of producing CPUs and such. You had companies like NEC back in the 1980s and 1990s producing their own CPUs and stuff, but a lot of companies dropped out, and Motorola was also in the game and companies like that, but they dropped out because it was very expensive to do, right, and complicated. So there's only a couple of key players that actually make CPUs and GPUs and stuff, like TSMC, which is based in Taiwan, and they make the most advanced chips in the world now. And as you can see, this line went up exponentially. As the nodes begin to shrink, you had more powerful CPUs. And this graph is based on transistor nodes from 1971 to 2023. So in 1971, we had 10 micrometers, which is about 10,000 nanometers. and it shrank all the way to 3 nanometers in 2023. That's the most advanced node that we have now. This graph, it shows, I have a graph of CPU MIPS from 1971 to 2023. MIPS basically means million instructions per second. This is how many instructions a CPU can execute in 1 second. So back in 1971, we had the Intel 4004, which was capable of 0.092 MIPS. Let me see how much that actually is. About 92,000 instructions per second in 1971. 1975, we had the MOS technology 6502 CPU, which was capable of 0.5 MIPS, about 500,000 instructions per second. 1976, well, I guess we'll start from here. Zilog Z80, 1.16 million instructions per second. And we'll go to 1985 at 386 at 4.3 million instructions per second. 1990, Motorola 6804 at 44 million. As you can see, this number just keeps getting higher and higher. And as I showed in the previous graph, the nodes for the transistors are getting smaller and smaller. So the CPUs are getting more powerful and smaller at the same time. With the Apple A17, has about 35 million, can perform 35 million MIPS, which is a very high number, which is a very powerful CPU in a small package. And as you can see, a Cray computer back in 1985 took up the size of a room, and it has less power than, I guess, any of these CPUs. It's got less power than, I guess, an i7 2600K, and much less power than a Apple A17. And you have a Fujitsu computer from 1993, which was a supercomputer. This has much less power than a Apple A17. I think it was capable of about 120 gigaflops, I think. And this is capable of maybe 1,300 gigaflops. So it is definitely less powerful. Let me see how much that is actually. Okay, so a Cray computer was about capable of 1.9 gigaflops in 1985. Fujitsu numerical wind tunnel was capable of 124.5 gigaflops. And an Apple A7, which is one of the most powerful CPUs out there right now, is capable of 1.789 teraflops or 1,789 gigaflops. So it is about 941 times more powerful than a Cray 2 computer from 1985. Is 14.37 times more powerful than a Fujitsu numerical wind tunnel from 1993. And if we compare this to a GeForce RTX 4090, which is capable of 8,258 gigaflops, it is 4,346 times more powerful than a Cray 2 computer from 1985. It is 66.3 times more powerful than a Fujitsu numerical wind tunnel supercomputer from 1993. So computers are getting more powerful, and they are definitely more capable. These capable today, because back in the 1980s, computers were very limited. You just couldn't do very much with it. They didn't have a lot of processing power. They didn't have a lot of memory, storage, or RAM. They didn't have a lot of connectivity. You didn't have like broadband internet or anything, so it's quite limited. But computers of today are very, very capable, especially computer processors. This includes GPUs as well. And I think it's going to lead to the AI revolution in the future, maybe in the near future. And I think it will lead to the replacement of many, many jobs in the future. People say there's nothing to worry about, it's just hype. I don't think it's hype. I think it will replace millions of jobs. I mean, if you think about it, you really don't need people programming computers and stuff like that, because if AI gets good enough, if it becomes good enough, like the founder of NVIDIA said, Jensen Huang said, you will be able to, everyone will be able to become programmers. Literally. Because all a computer is doing, I mean, you're using a programming language to communicate with the computer to tell it to do what you want. So if AI becomes good enough, you could just tell the computer what to do in plain English or whatever language, and the computer can do that. You don't need a computer programmer. It's like my friend back in the 1990s when I was going to university. He was a computer science major. He said, maybe in the distant future, nobody will have to learn computer programming, because you will be able to talk to the computer and tell it what to do. And computer programming, like he said, is just telling the computer what to do, right? The only reason why computer programmers had a leg up was because computer programming is not easy to learn. It's a skill that requires time and effort, and you need to have experience. But with the AI and more powerful computers, it's just not necessary. Just like travel agents aren't necessary today. You don't need them today. You got a computer. You could book your own flights connecting directly to the airline's website, right? You don't need that. There's a lot of jobs that aren't needed. I mean, have vanished as a result of all this technological innovations over the years. And you're not going to need a lot of people in the workplace, because if you could tell a computer or an artificial intelligence to just do a routine task by demonstrating it on, let's say, on this desktop, of just copying this and deleting it and sending it to this folder at this time or whatever. If you could get AI to do that, AI can do that. And AI could also write code also in the future. So you could have one person who's a programmer who knows what they're doing, and they could do the job of, who knows, 10 to 20 other programmers, and you don't need those other 20 people. And you'll probably have robots in the future which are going to be like in a human shape, and it could do stuff by you telling it how to do it, right? Without knowing all this complicated stuff. It could just identify, it could just see what you're doing. You demonstrate, this is what you do. This is how you make a French fries, like putting the French fries into the deep fryer, taking it out and putting it in this basket, something like that. It could be done. I'm sure it can. And I'm sure this is going to cause a lot of disruptions in the future. And this is what people are going to have to think about in the future as technology gets better and better. And who knows, they may come up with better chips using different type of technologies, like chips with graphene in it, which is faster than our current silicon-based technology. And who knows, they may even come out with photoresist chips, which is even faster than that, and you'll have more powerful computers as well. I remember watching this movie back when I was a teenager, back in 1991 or something, Terminator 2, how the Terminator's chip was a learning chip. It was a very powerful learning chip. I think that's what AI is. AI is capable of learning. And maybe in the future, you'll have a chip that is so powerful that it will be capable of learning and doing things. So I think this is going to be the future, but I would like to know what you think. And you could leave that in the comment section below. And thanks for watching.